All right, so let's start by importing the necessary libraries. So we'll be needing NumPy. So we import NumPy as NP. All right, just shortening it to NP so that we will not be writing NumPy over and over again. Then we will need pandas. All right, so we will import pandas as PD. All right, so going forward, we will be using PD instead of pandas. Okay, and then we'll also be doing some visualization. So we import matplotlib. All right, matplotlib.py plot. Then we will shorten it to plt, and then we will also be using seaborn. All right, we're using seaborn. So we import seaborn as SNS. All right, and then we'll be using matplotlib inline. All right, so that we'll be able to do our visualization inside the Jupyter notebook. All right, so let's run this and done. All right, so alternatively, we could have installed the Py first, right? Instead of doing this later on, also using with our algorithm, we also need to import different libraries. All right, so we could have just do pip install. All right, pip install Py first, and then in PyForest, from PyForest, from PyForest, we can import everything. All right, we could have done this by we could have used the lazy import, sorry. And then yeah, everything will be done, and then later on we will not be importing libraries over and over again. So PyForest will take care of everything. All right, from PyForest import everything, import, then use star. This could have taken care of everything. All right, because subsequently we are going to also import other libraries. All right, so by using this PyForest, all the libraries will be taken care of. The most used ones will be taken care of.
It's 1 o'clock.
All right, so I already have this. I'm not going to actually install it, so let me just comment it out so that you can use it when you get the Jupyter notebook. All right, so let's start by loading our data set. So we will create a variable and then we use it to store our data set here. So we're going to use pandas to read this. So pd.read underscore CSV, because our data set itself is in a comma separated format. So we are using the read underscore CSV. Had it been an SO, we use read underscore SO or any other format. All right, and then as I said, you can actually get this data set from Kaggle. All right, so I've already downloaded it, so I'm just going to read it. So I store it in this called breast cancer .csv. All right, so let me load this and then done. Now let's see the first 5 rows by using the head function. Right, now you can actually see the data set over here. Now let me just print, let me just do this so that we can see a lot of them over here. All right, so we have 699 rows with 11 columns. All right, different columns over here. So it's the same thing that we took a look at earlier on, right? Like ID and then clamp thickness, uniformity of cell size, uniformity of cell shape. All right, the same thing we have here: ID, clamp thickness, size, uniformity, and then all the way to mitosis and then classes. So you can see at the class we have is either 2 or is 4. All right, is either 2 or 4. All right, is either 2 or is 4. All right, so let me just print the head so that we can actually have space to do the rest of our work. All right, so I'm just printing only the first 5 rows. Okay, so going forward we can start by doing some data pre-processing. All right, so let me convert this one to a markdown and then use this and then write it over here. So we're going to do some data processing. All right, I'm going to do some data pre-processing over here. Okay, so let's try. I mean, with the class column, we can actually see how many are benign and how many are also malignant. All right, so in that case, we can use data, and then we just pick the class. All right, we pick the class column, and then we can actually count it. All right, by using the value, using this value count. All right, using value counts, we can actually count it. Now, if you see here, we have 458 being benign, or I mean, earlier on, if you remember, 2 represent benign, right? If you go to the original data set, saying that 2 is for benign and then 4 for malignant. All right, so if we see 2 is benign, right? So we have 458 benigns and then 241 malignant. All right, so let's check the data type, and then we can use data, and then we can use the D types. All right, okay, yeah. Now if you can see this, right, the data types is like almost all of them are integer, right? Except this, but let me mute this. All right, so except the bare nucleoli column, that is object. All right, except the bare nucleoli column, that is object. All right, and if we eyeball it, I mean, like almost all the column are I mean, they are all integer, right? So I mean, including the bare nucleoli, we can see that is supposed to be an integer, but when we check the data type, it's actually telling us that is an object, meaning that I mean, if we have 699 columns, I mean rows, right? 699 rows. So which means that there's something inside there which is preventing that column from being represented as an integer. All right, if we check, let me just give this here so that we can see the shape of it. All right, so here we are only seeing the first 5 rows, right? But if we are to go through everything, all the 699 rows, I mean all the 11 columns, and then the 699 rows, we will be seeing that with the bare nucleoli column, I mean, not all of them are integer, right? We are seeing integer here, but I mean, we are seeing all integer here, which, I mean, according to our own intuition, according to our, I mean, eyeballing supposed to be, this column is supposed to be an integer, but it's now giving us an object, which means there's something there which is preventing it to be an integer. So let's see that column. All right, let's see that column, which is I'm going to pick that. Let's see that bare nucleoli column. We pick this, and then we see that. So let's examine this. So I'm just picking this column. All right, I'm just picking only I'm just picking only this column where we have 1, 10, 2, 4, 1 all the way to 699, right? So 1, 10, 2, 4, 1, right? So let's just eyeball it and see if there's anything else which is different from an integer. All right, so if we go through, yeah, now if you see this part, all right, if you see the index 23, you can see that we have question mark there, which is not an integer, and that is why we are having an object here. That is why it's giving us an object. Not all data points in there are integer. All right, and that's why we're having that. So we can deal with this in several ways. All right, so let's try and pick that column and then show if we have only one, or there are others that are there, others that are also there. All right, so let's see all those rows that are having question marks in there with respect to bare nucleoli. Okay, so if we do this, we are going to have some true false. All right, So let me do this so that we can have a better look at it. All right, so this one now, if we go to the Bernoulli, we can see that there's a lot of question marks in there. All right, there's a lot of question marks in there. So about 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19, about 19 rows. I mean 19 rows are having these question marks represented, I mean, for Bernoulli, right? So when Dr. William was collecting this data, he represented question mark with unavailability of data. I mean, different researchers can use different symbols, or maybe even 0 to represent unavailability of data. All right, so you have to be very careful as a data scientist when you're preparing your data for machine learning algorithm. All right, in this case, you need to be very careful when dealing with it. Okay, so we can actually say that we want to maybe drop that. All right, maybe drop the rows that are containing these question marks. All right, and that should be your last option. Actually, that should be your last option as a data scientist preparing your data for machine learning algorithm. As soon as you drop any data point, you lose that information. All right, whether it's 1 or 2 or 3, you lose that information. All right, so dropping the data point should actually be your last option. All right, you can decide to drop these 19 rows, or maybe drop this column, the Bernoulli column, right? But whatever the case may be, remember we have 699 rows, right? And only 19 are having this, right? So if you say that, okay, it's maybe small, so let's drop it. You lose a lot of information. If you drop the rows, remember it will affect all the other columns too. And if you drop the this column, remember you are losing other information, which apart from these 19 question marks, all the other information, you will lose it. So you have to be very careful in dealing with this as a data scientist. All right, so another way that we could have used to examine this, instead of maybe printing all the columns, is maybe do something like this. And since the Bernoulli column is having it's an object or maybe a character and not a number, it cannot sum it, so that would be very obvious to actually identify. All right, if you can see here, it will sum all the other columns, but with that column cannot be summed. So you can easily see the whatever it is being represented. So even if it is 0 and it was represented in the form of a string, it can easily show you over here. All right, by using just the sum. If you can see this clamp thickness, right, this clamp thickness, it has summed everything over here and giving us a sum total of 54. The same thing with the other columns, but since this one is an object and it cannot actually sum it, it will actually output it, and you can easily spot it and see that there were some missing values in there, which Dr. William actually represented it with question mark. All right, and alternatively, we could have used the isTheGet function to also do that. All right, we could have used what is called the isTheGet function to do that. So let's try that one too and then see. All right, so as a data scientist, I mean, there are a lot of options that you can actually do. So isTheGet function actually show you if there's a digit in that column, all right, then it will output true, otherwise it will output false. All right, so if it's not a digit, then it will output false. So let's try and then do this. So let's say digits in this column. All right, we're trying to see all the digits that are in that column. So let me bring it here. Digits in this column equals let me put this thing in the data frame so that we can actually have a better look at it. So I'll do this, and then in our data I'll pick the Bernoulli, all right, and then use the str and use the isTheGet function here. All right, use the isTheGet function here, and then finally I'll close this. Yeah, so whatever this one is going to do is that it's just going to say that if you go through and then you find any anything which is not a digit, then you put false. But if it is a digit, put true. All right, so if you see this one, right, or if you see the column, this is the bare nucleoli column that we observed earlier on. All right, so everything here was a digit, right? Digit, or with the exception of 23, right? When we encounter 23 was not a digit. So the same way at 23 is supposed to give us false. All right, if you can see over here at index number 23, we're having false over there. All right, so you can also use the isDigit function to also get around this. All right, so let me comment this then. Let me comment it when you get the notebook. You can also do that, which is an alternative way of identifying it. All right, so let's move on, and then as I said, there are several ways of dealing with this, and one way is to drop everything, which should be your last option. All right, with Python, it's going to be very difficult dealing with the question mark. So, and Python understands the NaN, which is not a number. All right, so it will be easier for you if you replace this question mark with not a number, so that you can actually use the Python functions to deal with this. So, and that's what we're going to do here in our case, and that is just one of the ways, right? That is just one of the ways that you can actually deal with it. There are several ways that you can get yourself around this. All right, so we are going to replace, right? We are using the replace function, and then we are going to replace the question mark with np.nan. All right, so what we are saying over here is that when you see nan in our data, when you see when you see question mark in our data, replace it with nan. All right, when you see question mark in our data, just replace it with nan. All right, and that's what we are doing. And after that, we will store it in a new variable called df. Okay, we will store it in a new variable called df. So that is done. Let's just see df, and then see what is there. Let's print the head over. So df is just a copy of our original data, just that it's not having the question mark. All right, so let's do that. Now if we see over here, all right, if we see df is just the same thing. We cannot actually have a view of the question mark because this is just the first 5 rows. So let's pick that column, the bare nucleoli column, and then we can actually see that, right? So at first, at index number 23, right? At index number 23, there was a question mark there, and then we are saying that we are going to replace the question mark with nan. So at index number 23, you can see that it is now being replaced with nan. Now Python understands this nan, and we can actually deal with this nan. All right, so let's move on, and then actually perform further analysis on it. So as I said, there are several ways that you can deal with this, and you can replace this this nan with the mean of each of the column, or maybe the median of each of the column, right? In this case, we will use the median, right? We use the median to replace the nan with the median. So that we will not lose information. We will not drop anything to lose information. All right, it's better to replace it with the mean or the median, so that we will not be losing information instead of dropping it. So let's try and then check the median of each of the columns. All right, so if we do df.median, now we can see that with clump thickness is having a median of 4. With size uniformity with a median of 1, shape uniformity with a median of 1. Same for all of them. Now our column of interest here is bare nucleoli, right, with a median of 1. Okay, so what we are going to do is that for every nan that we will encounter, all right, for every nan that we will encounter, we're going to replace it with the median, right, and the median of that column is actually 1. All right, it's 1. So when we see nan, we replace it with 1. Okay, so let's move on and then do that one. So we're going to use the fill na. All right, we're going to use the fill na to do that. So df.fill na, and then we will fill it with the median. Okay, all right, so median. All right, so what we've done here is that whenever we encounter NAN, we are filling it with the median by using the fill NA function. All right, so now let's try and then see. Let's try and see it again. Okay, so let's go to to index number 23. Now you can see that index number 23 is now 1. It's not NAN again. In the same way with all the question marks which have been replaced with NAN, all the NAN are also going to be replaced with 1. All right, that's what's happening over here. Okay, so now if we check the data type again, data.dtypes, come on. All right, now if we check it again, we still have bare nucleoli to be object, despite the fact that we have replaced the question mark with 1. All right, we still have that column to be an object. So we're going to explicitly do this. All right, just creating the same column. All right, this is just the same column that we are maintaining over there. And then what we are going to do is that copy this and bring it here again. Okay, now we're going to convert this by using the as type. All right, by using the as type, the Python as type function, and then convert it to int 64, right? 64 bit. All right, so done. So now if we check the data type again, the df. Okay, over here we use the data, right? We're supposed to use df. All right, yeah. Now if we check it again, we can see that all is all is now integer. Now we are good. All right, we can now build the algorithm on it. All right, we can now build an algorithm on it. Okay, so what we are doing over here is that we cannot actually build an algorithm, machine learning algorithm, on a string or on our object. All right, we have to convert everything to an integer so that our machine will get to understand it. All right, the machine understands an integer instead of a string or an object. So when you have a data set that you want to perform a machine learning algorithm on it, you want to build an algorithm on it, then you have to convert that in data set, everything over there, everything in the variable, everything in the column, whatever it is, whether it's object or character, right? You need to convert it into an integer before you start building an algorithm on it. All right, that's what we are doing over here. Okay, so now that our data set is in perfect shape, let's start by doing some exploratory data analysis here. All right. Let me convert this to Markdown. Okay, so we can start by performing some exploratory data analysis here. Now, if I check the df.head, let me just print this so that we will still see our data here. Now you can see that we have everything to be an integer. Is very fine, but this ID, all right, this ID we don't actually need it. Okay, we don't actually need it. It's just an ID that Dr. William gave to the cells that he was working with, and we don't actually need it. It's not going to give us any information regarding our model that we are going to build. All right, so we're going to drop that ID. All right, we're going to drop that ID. So we use df.drop. All right, df.drop, then we drop the ID. All right, then we specify over here, we specify that the ID is found in the column. All right, so we use axis equals 1. Okay, now if you use axis equals 0, then you're specifying the row, but if you use axis equals 1, then you want to show Python that go to the column and then find this index over there and drop it. Okay, now if we do this, right, this changes that we are doing is not actually going to reflect in the df data set. All right, it's not going to reflect in this. So one thing that we can add is in place equals true. All right, we can write in place equals true. In fact, let me do this so that you can actually see it better. Let me just run this. Now you can see that the ID is no more there. Right, it's starting with clamp thickness and then size uniformity, all the way to class. All right, the ID is not there. You can see it's over here. There's no ID, but still, if we check the df, let's check the df again. Let me check the df. Let me just print the head of it. You see that the ID is still there. All right, so the changes that we made up here is not actually reflecting in our data set. So in that case, we need to add in place equals true. Come on, okay. In place equals true. All right, so now if we check again, come on, okay. Now it's not there. You can see that now if we check our df, you can see that now the ID is no more there. All right, it's not there. Now the changes that we made has now reflected in our data set. Okay, so now from here we can actually start by actually seeing the 5-number summary. Okay, we can see the 5-number summary, which is the minimum, the maximum, the 25th, the quartiles, right, which is the 25th and the 75th and the 50th. All right, we can actually see it by using the describe function. So let's do describe over here, and then you can actually see that let me just transpose this. Let me transpose this so that we have a better view. Yeah, this is quite better. Now you can see that we have the count of each of the columns. We have 699 for each of the columns. All right, and then we can have the mean of each of the columns. We have the standard deviation of each of the columns. We have the minimum of each of the column with the maximum here, and then the Q1, the Q3, and the Q2. All right, and this, this actually tells you the variation in the data set. If you see the standard deviation is quite uniform for all of them, right? It's not that each column is not that different from each other, depending with regards to the data set that we are working on. All right, they're almost similar, maybe ranging from 1 to say 10 or something like that. All right, unlike a data set like this, let me show you a different. Yeah, unlike a data set like this that you have some which is around 95, a bit low, but some are going all the way to 178. All right, 178. Some are a bit low, like 70. Some are even 6. All right, just two different there's a two. It's way wide. All right, if you see the describe function here for that, you can see that some are 2, the standard deviation 6, and some are all the way to 176. All right, so in our case, with the one that we are working on right now, it's a bit uniform. All right, it's a bit uniform. Okay, it's a bit uniform. You can see that almost all of them are around 2 or 3, right, with some 1 and then 0 over here. All right, so in this case, you can see that is a bit okay to work with. But if you have a data set where the variation is too much, then you need to do a lot of stuff over there. All right, now we will do a sample in the live class and you will get to know that. Okay, so let's move forward by doing some bivariate. All right, some bivariate analysis over here. Let me convert this bivariate data analysis. Okay, let me convert this to Markdown. Maybe probably like that. Okay, so since our target here is is the class. All right, let's try and then see the distribution of the class column. Remember, we imported cborn as s and s, so I'm going to use that to make this plot. All right, so I'm going to use this plot to actually plot the distribution of the class column. All right, okay, so cborn has no attribute this plot. It has. Okay, so now you can see over here that we have, it's either 2, that is for benign. All right, you can see over here it's either benign or it's malignant for the class column. All right, it's either 2 or 4, and you can see the KD being plotted here. I mean the kernel density estimate, which is showing the uniformity in each of these 2 different categories of cells. Okay, so we can also do the same thing for all the other columns, right? So let me do that, which will be a multivariate data analysis. So all these are part of exploratory data analysis, which as a data scientist you have to do and then get familiar with your data that you are working on. All right, so that you actually get a good data to make a good model, right? Otherwise, if you just start building the algorithm, you might end up having a very false model, which will not work on production. All right, so you need to actually get yourself familiar with the data that you are working with. So I'm going to use the histogram. I'm going to plot a histogram of all the other columns, right? So let me set this bin size to say 20. All right, let me set it to 20, and then set a figure size. So fixed size, let me set a fixed size to say let me give it 30 by 30. All right, let me give it 30 by 30, and then I can also set the layout. All right, set the layout to 663. That's fine. All right, so let me run this. What happened? Rectangle object has no object bin. Okay, supposed to be bins. All right, that's it. Okay, so it's plotting. Yeah, but I don't like this thing that is showing over here. All right, so let me just get around with it by putting this there. All right, cool. Now it's looking a bit okay. So these are all the histogram for all the other columns that we have. So this is almost the same as what we did for just the class column, right? If you can see over here, we have for the class column, we have only 2 categories here, whether it's benign or it's malignant, right? Whether it's 2 or 4. All right, the same thing for all the other columns. We've been able to actually visualize them, and you can see that most of them are having their values around 1. All right, that's why you can see a Spark here have a lot of 1 values that are very, very high in each of the columns. All right, if you can actually even see it over here, we have a lot of ones in there, so that's why you can see a Spark at the one bar over here. Okay, we can also even use the box plot. We can use the box plot to confirm this. So we can use, let me set a figure size here, fixed size. All right, let me set a fixed size over here. Let me just give it like 15 and then 10. All right, then I'll use cborn. Then I'll use the box plot, and our data is df. All right, so that's fine. Okay, let me just try, and then you see that the ticks over here are actually not it's just being clumped together. Let me just turn this to let me change the orientation. So orient equals, let me make it horizontal. Yeah, now it's a bit better. Now you can see it over here. Now, as I said, most of them are having their values at, at 1, and maybe between 1 and somewhere 5. All right, with maximum data point over there to be 10. All right, so and you can see some are having their maximum maybe around 8, with some 2 outliers in there, right? Not that much, so it's not actually going to hurt us that much. All right, so it's a bit okay. It's a bit okay with respect to the kind of data set we are dealing with. All right, it's not like it's not a big data set that we can worry about, and with the kind of uniformity in it, is okay to move on. All right, we are not actually going to remove any outliers in this case, because it's not that much. These 2, 3 is not that much to actually hit our algorithm. All right, but if it's a data set like the one I showed you earlier on, which is a bit complicated data set, and we actually reduce the size of it by using the principal component analysis, and then even the data, the outliers, if you can see over here, there is a lot of outliers in there, and if you use this to build an algorithm, it's actually going to hurt your final model. All right, so in this case we dealt with it, but with the one we are dealing with right now, it's not that it's not actually going to have a big impact on our model, so we can actually proceed with it. All right, we can even check the correlation. We can check the correlation and see. Let's use the call function to check the correlation. All right, so if we see the correlation here, there's a correlation matrix that we've been able to plot with the df.call. All right, so obviously the diagonals are going to be 1. All right, the diagonals are always going to be 1, and if you can see here, maybe it's almost, not almost, I think all of them are positive correlated. All right, with some very weak and some very high. All right, as high as 0.9, which is size uniformity, and shape uniformity, which is very, very high, positively correlated. All right, and I think let me go down here. Maybe 0.81 is also very high, which is class, and then class and shape uniformity. All right, so the columns here are positively correlated. All right, positively. Some are very weak. A little bit above 5, and yeah, I think yeah, the very weak one here, 0.3 here. All right, very, very weak here, which is mitosis and clamp thickness. Okay, so let's try and then have a heat map of it, and we can actually also have a visualization of this, which will be a bit clear for us to understand it. So I'm setting the figure size. So in this case, figure size equals, then I can give it to be maybe 35, 15. That will work. Okay, then I'll use the seaborn dot heat map. All right, so inside the heat map, I use df.call, that's the correlation, right? I'm going to use this correlation to actually do the heat map. Actually, I want it to be square. Then I will allow annotate to, so that I will actually see these correlations on the heat map. All right, so I'll set this to true. close it finally, and then I can set the title, right? Dot title, and then I can call it correlation between, no, amount rather. Let me use that. Okay, I think this one was the right choice, since we will compare the correlation between two of them, all right, with each pair of it. Okay, then finally I will use plt dot show. Okay, let's see what happened. Okay, so where is it? Good. Okay, so as you can see over here, this is the same correlation that we've plotted over here, right? The same correlation we have used the heat map to plot over here. Okay, so if you see the bar over here, the more the color goes to yellow, the higher the correlation. All right, so as you can see, the diagonals is very, very yellow in color. All right, and that is just a correlation between an attribute and itself. All right, like damp thickness and damp thickness. All right, that will give you a correlation of 1, which is of no use to measure a correlation of an attribute and itself. All right, however, you can also see some of them with high correlation that are a bit yellow here, 0.82, which is size, uniformity, and class. All right, and you can see also from bare nucleoli and class is high. You can also see 0.91 here, which is size uniformity and shape uniformity, 0.91. You can confirm the same from here, size uniformity and shape uniformity, 0.91 over here. Okay, so that is what the heat map actually helps you to do. Visually, you can actually see the correlation between each of these attributes. Okay, you can actually have a visual view of each of these attributes. Okay, so we can also use this the pair plot. All right, we can use the pair plot to actually have the distribution of all these attributes. All right, so I'll use our data set here, sns.pairplot, then I'll use our data set here, and then the diagonal. Right, for the diagonal of the pair plot, you can actually specify what you want. So the diagonal kind, in this case, it will be good if we use the kernel density estimate. All right, so we're going to use that, and then we will get our pair plot. So it's actually running. It's taking a little bit of time considering the number of columns to be 11. All right, it's taking a little bit of time. Then after that, we are actually going to start building our algorithms. All right, so let me do this so that we have some break here, and then let me write here building our model. Okay, so now it is being plotted. Now you can see over here, right? This is the same correlation that we have here that we've plotted in. We've been able to use pair plot to plot it over here. All right. So this diagonal, this is the kernel density. If we don't specify, by default, it's going to give you a histogram. All right. But this actually gives us an idea of how many clusters that we have in there. So you can see over here that we have 2, 2, 2, 2, 2. 2, 2, 2, 2 over here, 1, 2, 1, 2 over here. So this one is actually giving you an idea that these features are actually going to help you to predict into two classes, whether benign or Malignant. All right, and you can see that the correlation is a bit positive correlated by very weak. All right, very weak positive correlation among the various attributes. Okay, very weak positive correlation among the various attributes. So we start by building our algorithm over here. All right, let me convert this to a markdown, maybe make it a little bit bigger.